Hi, I'm Ronak, member of the perception team, and I'm going to be presenting some work that I've been leading on using FairMOT, which is a tool that I'll go into some more detail on for high-speed race car tracking, which is what we're going to be doing here. So I kind of want to frame the challenge of what is tracking exactly in the context of what we're doing here at Driverless. And the first thing that you might think of that kind of is logical when you think of tracking is that you want to draw boxes basically around the objects that you're seeing. So on our race car, we're going to have some various, cameras. And what we're going to want to do is while we're driving around, especially for the IAC challenge, we're going to want to know where the other race cars are with respect to us. And we want to send that information to the other teams, specifically like planning and controls, so that with that information, then they can make the best judgments about how to route our car around the other vehicles or how to maybe overtake them. So it's really important that we have really precise information about where the cars are at any given point of time relative to us. But more than just tracking the locations of the race cars, which here is kind of shown with these bounding boxes, that you can kind of see. More than just that, we also want to get an idea of the identity of the race cars. And what I mean by this is that we want to try to figure out the difference between if two race cars, let's say, are driving right next to each other and one overtakes the other. We don't want to kind of mix them up. We want to know which race car is which, because that can really help the planning team kind of come up with trajectories for the other cars that we're dealing with. And with these trajectories, then they can kind of get an idea for what the other cars are doing, and then we can plan around that and improve. And not only do we want to keep track of the identities of these cars while we're watching them in our video, we also want to keep track of their identities if a car kind of leaves the frame and then comes back in frame. We want to know that this is the same car. And so it turns out that this second part of it, keeping track of the identities of the vehicles, actually adds a significant, greater challenge to this whole process. And I'll get into some more details on how we address that in a bit. So to start, I just like to highlight some of the really popular solutions that have been in the literature until now. The most popular and I would say straightforward method is to pair an object detection method with a real-time tracker. So what I mean by that is, let's say you have a series of images here that can create a video basically of cars moving or any objects moving. The traditional method is to take an object detection method. Now, these object detectors are you might be familiar with them. There are some like YOLO or faster RCNN. And usually the way that they work is with an anchor-based method. And what that means is they take an image, they split it up into kind of grid squares or rectangles, and they try to identify in these squares where an object is. Is there an object in this square? If so, what object is it? That kind of information. So what this allows you to do, what this object detector allows you to do, is it allows you to generate a map like this. So this would actually be an object detection map in that you get the race car positions in a given single frame. And then this information about where the race car positions are then aggregated through something called a real-time tracker. And this real-time tracker is basically looking at the positions of the cars in the image. And over time, it looks at how it can associate various boxes to each other to form a trajectory. And I can go into a little bit more technical detail if you're interested, but the main features it uses is how close is this box to the box that was in the previous frame? Okay, if it's really close, then it's probably the same object. And also, what are the visual features of the object across these two frames? It can kind of integrate information about the visual similarity of these bounding boxes that are drawn to kind of get an idea of how to associate the boxes together. But as you might guess, this is a pretty inaccurate way of actually doing this prediction. One is because the object detector isn't actually involved. It's like a separate agent from the thing that's actually determining what it's separate from determining the positions of the bounding boxes and how the bounding boxes relate to each other. So it's pretty inaccurate. It's not anchor free. It doesn't have Re-ID. And this Re-ID is the problem that I mentioned before of if an object exits from a frame and then re-enters the frame, you want to be able to re-identify it as the same object. So that's something that's kind of important in building trajectories and in predicting. So there are a lot of problems with this method, but I would say that the greatest problem is the fact that you have a separate object detector and a separate real-time tracker, and each of these are expensive computationally. So the biggest problem is the inference speed. I mean, we have, especially here at Driverless, we have race cars that are going at really, really fast speeds, and we're going to be going at really fast speeds during the IAC competition. So the race cars go fast, and we have that object tracking methods are pretty slow, especially the ones that I just described, because we're separately doing object detection and then taking more features out of the object detected regions and then computing more operations on them. So by the time we do all of that, the race car is going to be in a different position altogether. So the information that we just collected is not going to really help us make a decision. We need to be doing this in real time at a pretty fast inference speed. So how can we address that? One method that has been proposed in the literature is called CenterTrack. And this is something that we did seriously consider using initially when we were starting with this project. But the idea behind CenterTrack is that rather than predicting the bounding boxes separately, it actually predicts 3 features with one neural network and is then able to actually create the bounding boxes with ID assignments saying that this bounding box is car number 1, this bounding box is car number 2, etc. We're able to do that in one pass of a neural network, which is a lot faster than before. And the main idea behind it is that rather than actually using a anchor-based solution, it instead predicts the location of object centers. So it creates a map. So if you're trying to predict like the location of people in an image, you can kind of see that there's the silhouettes of 3 people in this image. And the network is actually going to predict the center points of these people in the image. So you can kind of see here that the center point is located right on the middle of this person, right on the middle of this person, right on the middle of this person. And in addition to that, it also then predicts the size of the objects that you have in each of these locations. So with the size information, it's then able to actually reverse engineer a bounding box. But the best part is that CenterTrack takes 2 images at a time. It takes the current image and it takes the image from the previous frame. And like, why is that relevant? Well, the relevance is that it also computes an offset. And this offset is a critical thing for how CenterTrack works. The offset basically is looking at what is the distance between the object center in this frame, in the current frame at t equals t, and between the object center in the current frame and the object center in the previous frame. And the idea behind that is that if you have an offset, if the network itself is predicting an offset, this is where this object was in the previous frame. Well, we have the object centers in the previous frame. So you can use a simple greedy algorithm, which basically all that's doing is it's looking for what object is closest to the offset vector that was found. You can use a simple greedy algorithm to predict the bounds and get IDs. So also, I just wanted to mention, if anyone has any questions, please just stop me at any time and ask, because I'd be happy to go into more detail or answer anything. But
I got a question.
Yeah, sure.
Yeah, since you gave the opportunity. So, like, how good is this at tracking path? So, like predicting or like the path this person is going to take or the car eventually will take?
Okay, so that's a good question. The problems that we're like addressing in this presentation are not trajectory prediction, but actually object tracking. So tracking is basically looking at what information you already have, not actually looking at the future. So what this method could do, though, is actually generate trajectories. This is what the object is currently doing. It's moving from this coordinate to this coordinate to this coordinate. And with that information, you could then construct a trajectory and feed that into a separate model if you're interested in trajectory prediction. And that separate model could then predict what the next trajectory point is going to be. But this is only looking at the information we already have and not kind of trying to predict the future. Does that make sense?
Yeah, thanks.
Okay, no problem.
Here on a quick question.
Yes.
What is t-1 here? What is -1? Is it time or is this the previous frame?
The previous frame, yeah. So like I just said t equals t here is referring to the current frame, and t equals t-1 is the previous frame. So if you move one time step backwards, then that would be the frame previous to the current one. Okay, so I guess I'll move on. And there are a couple of issues with this. One is that it's still not completely optimized, in that there's a little bit of slowness in terms of this greedy algorithm. You need to kind of compute the, you have to iterate through all of the different object centers and look at this offset information to try to predict the closest match. But it's still pretty fast. I mean, this would be acceptable probably in terms of what we need for inference on our team. The main issue with it is that it doesn't have the capability for doing Re-ID. You can imagine that when the object is going to go off screen, it won't have an offset vector to map to. So there won't be any object center present if the object is gone. So it's not able to actually do Re-ID at all. And when I say here bad at transfer learning, I guess I wouldn't say it's bad at transfer learning necessarily. It's just that when you change from one object class to another object class, it's been shown that CenterTrack takes like a lot more training data to actually to transfer and learn a new object class, because it's basically the offset vector kind of learning this part of it is complicated, and it kind of differs based on what object class you're predicting. So if you're predicting people versus cars, it takes kind of a lot more training data to adjust it to that, has been shown. So kind of this is the second problem, I guess. And that problem is data availability. We want to operate in a setting where we don't have a lot of data. We want to take a pre-trained model, tweak it only just a little bit, and be able to operate on our problems that we're interested in, be able to do trajectory prediction on cars rather than whatever it was predicting before. This is specifically important because IAC has been very vague in terms of their communications about what kind of data the perception teams will be receiving. We are not sure what magnitude of the data we'll be receiving. We have been somewhat promised that we're going to get, I think, cars driving with other cars, but is that data going to be labeled? We have no idea. So we need to prepare for the likely worst case scenario in that we're not going to get a lot of data from IAC, and we're going to have to deal with a low data situation. So to address that problem, we are going to want to use an architecture that has been shown to transfer really well. And also, again, we have that same problem as before. We want to be conducting inference as fast as possible and as accurately as possible. So the architecture that we finally settled on is called FairMOT. And the way it works is that you take an input image, and it predicts very similarly to CenterTrack, I believe. It predicts the object centers. It outputs the box size, and this is basically the height and width. And here the center offset is actually not the offset from, it's not the same as this offset over here. This is a different center offset that they actually show improves the training accuracy. So what this center offset does is it actually shows that if the heat map predicts one center, then the center offset basically says, oh, shift your center over a little bit more to the left or to the right. And this has actually been shown to improve the accuracy of detection for kind of various reasons that the paper goes into way more detail on. But there are a lot of advantages to the solution. The main thing that it does, though, that the other techniques that I've shown up till now do not do, is Re-ID. And what Re-ID is, as I mentioned, it allows the system to be able to, if something disappears from frame and then reappears in the frame, it can still detect it as the same object. And the way it does this is it extracts an embedding from each object in the image. And I can go into a little bit more detail on this, but the encoder-decoder architecture over here, it outputs from this image basically a compressed representation of your data. And with this compressed representation, the network is actually able to, in kind of one fell swoop, compute the heat map, the box size, the center offset, and the Re-ID embeddings. And the Re-ID embeddings, what they are is for every box in the image, and it actually does this for every point in the image, but for every box, let's just consider every box in the image that has been identified as an object, it extracts a feature embedding, these vectors over here, and now it stores these vectors into what you can think of as a database. And now anytime you have a new detection, all you do is you compute the nearest neighbor to the embeddings within the database. So what I mean by that is you look at, if there's a new box that's been detected, let's say around this orange person over here, you extract the Re-ID features from that box, and then you're able to basically look up, have I seen any features that look similar to the Re-ID features that I've identified from this box in the previous frames? And if you do identify it, identify an embedding that's very similar, then you can actually you can assign it the same object class. So what I mean by that is you can assign it the same ID as this is person number 1 or this is person number 2. And if it disappears, no problem, because the embedding is still stored within the database. Now, the way this works a little bit more technically is that you actually have the Re-ID embedding like fork of the network. This is one network architecture that kind of breaks off into different branches. So the Re-ID branch of this network architecture actually outputs an entire image, but an image of, let's say, channel size 100. And what that means is that every pixel in the image has 100 values associated with it. And those 100 values are the Re-ID embedding for that specific pixel. So once the detection system actually identifies the center points for the for the detections in the image, all you actually do is you just look at the Re-ID embeddings for that specific center point within the image. The traditional approach when you do Re-ID is to actually train a separate convolutional network to operate on just the area that's been extracted. But you can understand that that's way slower because you have to run these two things kind of not in parallel, but in a cascaded fashion. And that greatly slows down your inference time if you want to do Re-ID. Because you're going to have to first extract the boxes around each individual or every car, and then take those boxes and then feed them through another neural network that extracts embeddings that you then look up. The advantage with this approach is that it does it all in one pass, and then you can reference it, and then you can use this information to make the prediction. And this is a really popular approach in the machine learning literature. Goes back to like 1988 paper by Caruana, where he proposed something called multitask learning, where you have multiple tasks that you learn at the same time. Some are called the primary tasks, and some of them are called the auxiliary tasks. So you can consider the Re-ID task as being an auxiliary task. And the great thing that they found is that although this actually makes things faster, this auxiliary task of Re-ID embeddings actually improves the accuracy. So FairMOT is actually at like the state-of-the-art accuracy on the object detection and object tracking benchmarks. Even if you ignore the Re-ID part, if you just look at the detection, it's actually comparable to all of the existing state-of-the-art tasks. Okay, so was there a question?
Yeah. Hey. So I just had a question. I was thinking about this, applying this to the IndyCar and head-to-head. And I was just thinking about like if those two bounding boxes there were cars, obviously, right? Like how often does this, I don't know if it refreshes or do you start over or how long it tries to track an ID. So I'm thinking about cars quickly moving in front of us, like one car, like maybe the blue box comes in front of us and replaces pink, and they kind of like swerve back and forth, like who's in front and who's behind.
Yeah.
That's probably a potential, that's like a potential scenario, right? That could happen. So I'm just curious, like how it manages similar shapes, right? They're like really indiscernible.
Yeah. So the idea is that Yes, you're right in that the objects will probably be kind of similar in terms of the shape. But if it does actually, I didn't go into the complete details here. It's not simply a nearest neighbor search with the feature extraction. It actually takes the feature extraction as one distance metric, but then it also does integrate information about the position of the bounding boxes, and it uses a Kalman filter actually to integrate that information about the re-IDs and the positional information to then make a prediction about which bounding boxes are associated together. But the main advantage is that you don't need the positional information per se in the previous frame to make your decision. You can potentially classify an object if it kind of disappears and then shows back into frame if it has like a very distinguishable object ID, if that makes sense.
I think the challenging part for Re-ID for IIC is the back view, front view, and side view of IndyCar is so different, and our camera is facing 5 different angles, so the perspective might be a challenge for us.
Yeah, so that's something that we can look into. One potential thing that I was thinking about, a way that we could kind of mitigate that is by actually taking pictures of the cars from from different perspectives beforehand, and then pre-populating the Re-ID database, I guess, with these cars in different positions. And what we could do with that is that we kind of create a database of embeddings for like a team number, whatever. And with that, then we can predict better the...
I guess essentially we just have a database of different teams' cars, so that we can formulate as a like classification problem of different cars before we
exactly.
Is there do you guys know if there are different, like the cars are the same or if they look different? Because it makes sense, or the mapping estimation where like I think we're dependent on this part of your project, but it's unclear if it's actually possible to ID cars if they all are like built the same.
Yeah, that's a great question. Basically, there are like stickers and other kind of distinguishing marks that I've seen from the videos I've seen so far, at least in the competitions that I've looked at. So I don't think that the cars will be completely identical, but let's say worst case, they are completely identical. Then the only con to this approach is that the Re-ID features won't be very useful, but it'll still have the motion tracking features, and it will be able to kind of it'll be able to use the Kalman filter to integrate information about the position of the vehicles. So you'll still get trajectory information. The only thing is that the Re-ID is like a bonus feature. It basically gives you a better idea of which car is which when it exits the frame and when it enters the frame. And I think that it's nice to have, but if for some reason it's not possible, if the cars look too similar, then it's okay, and you can just rely on positional information.
I think you will most likely have each team get to have their own print, like for all purpose, like even for PR purpose of the competition. You want to have a competition of different colors of cars on the track.
Exactly. Yeah. Okay. So I think that is most of the description of the architecture. Unless we have any more questions, I can kind of move into how I trained this model on what data, and then I can give you guys a demo. Is that okay?
Lovely.
Okay. So the data set that we used was Kitty. And we understand that there's lots of other data sets that are out there for object detection with cars. But we chose Kitty for the specific reason in that there's very few data samples that are available that are annotated. It's an amount of data that we would probably be comfortable annotating ourselves or outsourcing to like Mechanical Turk for a pretty low price if IAC just gives us a bunch of unlabeled footage. So we wanted to verify that, yes, we're able to do object detection on a small data set and it works with reasonable accuracy. The second is that it has 2D bounding boxes of cars. A lot of the other data sets are built for like 3D object detection, which we're not kind of targeting with this approach because it's kind of slow in most of the methods that are popular. Okay, so let me just wait for these videos to load. And I'm gonna actually, I think I forgot to share with optimized screen quality. So let me stop sharing and then reshare for a second. Okay, no, I did actually optimize it, never mind. So here, I'm gonna play these two videos at the same time, but I just wanna prepare you for what you're seeing. On the left, you're gonna see a video that is taken straight from the Kitty test set. And this video is, it's just a standard road driving scenario. But what I also wanted to investigate was how the FairMOT model for object tracking fares when you are when you're encountering a problem with dropped frames. And we basically wanted to simulate the racing conditions, because in 1 second, in a racing situation, when you're going 180 miles per hour, a lot more changes than in 1 second when you're going at the standard pace. So dropping frames basically simulates what high-speed driving is going to look like better. And that's the goal with this evaluation method. So hopefully you'll see that the object detections are kind of similar between the two, but obviously on the left, because we have more frames, more data, you'll see that the tracking is a little bit better, and probably the object Re-ID is also a little bit better on the left. Okay, I'll play it now. Are you guys able to see that?
Yes, sir. So each car represents one ID.
Exactly. Yes. So every car represents one ID. So what you should be seeing is that the bounding boxes around the cars are not changing. So like the green car is the green car throughout, basically. It's labeled with a green box throughout. And you might see it actually change in like once or twice in the frame, especially with the simulated racing conditions. But the idea is that ideally we won't actually see this behavior of like any changing ID for the cars. And also, as far as I understand, the planning team will probably have some protocols in place to kind of make sure that the object IDs that we're sending them make sense and that they're within some close distance to each other, to kind of verify that we're not mixing up the cars. So we'll do our best on our end, on the perception end, but on the planning side, they have some more algorithms, I would probably guess, to kind of verify that the trajectories are indeed the correct trajectories given just the object points in 3D. Okay, so I can play this video one more time if you'd like.
Could I comment on that a little bit? I know the planning team doesn't currently have any plans to do such a thing.
It's the state estimation team that cleans everything up.
Okay, yeah, sorry, that's what I meant. State estimation.
Okay, that would make a lot more sense. Thank you.
I'm still a little bit new to the team, so I kind of mix up the different groups sometimes. Sorry.
Oh, don't worry.
So should I play this again, or should I just move on to the conclusion?
Play it again.
Yeah, if you can play, that would be great.
Okay, I'm going to play it one more time. Okay, and I understand it's kind of fast, but it helps to look on the left side to get a better picture of the thing. But you can actually see the condition in that some cars kind of disappear from frame and they reappear and it still shows up. Okay, I'll share a link to this presentation, by the way, so you can view the videos again if you want to later. But the last thing I just wanted to talk about is the next steps from here. So this was evaluated on like a fancy server when I was running all of this stuff and training it. But in order to get it on the cars, we need to optimize it a little bit more for inference. And that's probably some work that Christine and Gianna from the perception team are going to be leading. And the idea is that we're going to be taking the car, we're going to be porting it into ROS and TensorRT. And what that will allow is for like a little bit more optimized computations on the whatever platform we're ending up using for inference. Ideally, we can get this running at like 30 FPS or higher. And the second part is a little bit kind of further off in the horizon, but once we get some data from IAC, we're going to want to do some kind of data annotation. And yeah, that's the second part of it. So with that, if you guys have any further questions, I can answer that, or we can kind of go to team updates, technical questions for the team leads.
How does this play in with depth estimation, or like actually producing tracking results in 3D? Because the state estimation team is looking at doing similar sorts of tracking. So like Jose and Jordan can speak more to that. They're looking at doing similar tracking, but in 3D space and from several different types of sensors. So it would be possible, for example, it would be helpful for us to maybe access the Re-ID embeddings, and maybe we can move a Re-ID stage to 3D as opposed to 2D or something like that.
So the idea that we were considering for getting the 3D position information is interfacing with the LiDAR data. But the LiDAR data is kind of expensive to do a lot of computation on, and this is a pretty large network, so we wouldn't want to actually do the object detection within LiDAR. But the idea here is to kind of have a more efficient solution. We're going to do the object detection in 2D, and then we're going to look at the region of interest, and we're going to maybe take an average of the LiDAR coordinates that we get. If we can kind of map between the camera data and the LiDAR data, if we can get that calibrated properly, then we can look at the region of interest in LiDAR. And then after we kind of get like a two-way mapping between the 2D cameras and the LiDAR, and that will return actually the position in 3D coordinates of the object. Does that answer the question?
Yep. Yeah, that should work. We've done this before. It's hard sometimes. Turns out just vibrations are enough to affect where you think the cameras are pointing relative to the LiDAR. So we'll have to see.
Another benefit though that we do have is that in our case the camera data is, the object of interest is a lot bigger than when we were detecting cones. So we potentially have more room to play with in terms of calibration accuracy.
Apart from, let's say, the data that you actually require from IAC to see if all of this works or not, is there some initial steps that we could probably ask IAC to verify, I don't know, in terms of hardware or just basic stuff to get things rolling? Can you think of anything?
So SIBO, I think maybe can comment a little bit more on this because I'm not sure what information IAC has shared. But as far as I know, I think we know the compute platform. I think SIBO mentioned what GPU we're going to be using, and it should be more than capable of running this software. And in terms of the data that's required, I think we just need multi-agent racing data. And if we can't get that from IAC, we can get it from other places in the worst case.
Okay.
Yeah, but other place most likely means it's only gonna be camera data. So you know our sensors also comes with LiDAR. It's hard. Then probably right now we can only develop camera-based perception due to lack of data. Yeah, on LiDAR.
For sure. Okay. Any more questions, or should we stop it here? Okay.
Yeah, very very nice presentation. Thank you.
Yeah, amazing, Ronak. Congrats, man. That was really, really good. And I think we should actually give Ronak a hand as also a way of finishing the meeting, unless there's anything else anyone wants to bring up. But yeah, if you can turn on your cameras and join me in like one ceremonial clap to Ronak, that would be appreciated. So on the count of 3. 1, 2, 3. There you go, Ron.
Thank you, guys.
You got a clap. Nice seeing you all. Great work, man.
Have a good weekend.
Great work.
See you on Saturday.
Oh, yeah.
Great work, Ronak.